Hello, in this video I am going to discuss the second method for estimating infiltration, which is the Horton model. So the Horton model is an empirical relationship that assumes that infiltration begins at some rate, which we call FO, and then exponentially decreases. So it has an equation. Let's look at the equation. So the equation says that F sub T is equal to F sub O, the initial infiltration, minus F sub C, e to the negative KT, so you'll see that exponential come in, plus F sub C. Here's the equation, and let's define each of the terms. So F of T is the infiltration. I'm going to summarize this as infill at time T. F of O is that initial infiltration. And this is at time 0. F sub C is the minimum infiltration. So this would be the infiltration at some time equals infinity. And K is the decay constant of infiltration. So this is going to be different for every watershed. The units on all of our F's, our infiltration, are inches per hour. And the units on that decay constant are 1/hour. Now we're going to look at an example and apply Horton's model of infiltration. So you can find this example in the handout for infiltration. And so we're going to go through this here on this video. So first we're going to figure out A, B, and C, developing the equation, and then we'll derive a table similar to what we did for the previous method for part D. Okay, so first, what is the initial infiltration? So we're going to get this value just by looking at our graph. So we can see that at time 0, the infiltration is 12 inches per hour. So that's going to be our initial infiltration. And part B, and I'll write these in a second, part B asks us to find the value of the saturated hydraulic conductivity, which is F sub C, or the infiltration at time infinity. And so we're going to read that from this value down here. So where the value that the infiltration approaches as time goes to infinity. Okay? So the answer to part A is F sub O is equal to 12 inches per hour. Again, we read that right from the figure. And then for part B, F sub C is equal to 1 inch per hour. And so we're going to come to part C now, where we develop the equation. So I'm going to start this by writing F of T is equal to 12 minus 1 e to the negative kt plus 1, which I can write as 1 plus 11 e to the negative kt. So at any time t, your infiltration can be estimated as 1 plus 11 e to the negative kt. So to use this equation, though, we need to figure out we need to figure out the k, that decay rate. So I'm going to look back at my graph and pick out another point. And so I'll write it down here first and then go mark it on the graph. So I'm going to use F at time 0.5 hours is equal to 6 inches per hour. So looking back at that chart, I've picked out this starred point here, which is at 0.5 hours and has an infiltration rate of 6 inches per hour. Okay, so if I know that, then I'm going to write 6 is equal to 1 plus 11 e to the negative k times 0.5. We can solve this math. We would have 5 over 11 e to the negative k times 0.5, And we would get, using ln eventually, that K is 1.5771 over hour. So last step here, I'm just going to write that equation out. We are going to have, for this particular storm or watershed, f of t is going to be equal to 1 plus 11 e to the negative 1.577 times t. So to solve for part D, we're going to use the same approach where we made a table as I did in the other example. So I'm going to go to a new slide to do this. Okay, so we are going to estimate the runoff using the Horton model of infiltration. And you should recognize this storm as the same example from the index method storm. And so we're also going to apply this to the same 100-acre watershed. So I'm going to do this by setting up a table that we'll fill out together. So I've set up this table, and I'll explain each column. So the first one is the interval begin. So that's the time at the beginning of the interval. Interval ending, that's the time at the end of the interval. And then I'm going to use those times to figure out with my equation the beginning F infiltration, the ending F, and then I'm going to just use an average of those two values. And then I have I, which is my intensity of the rainfall for that same period. Then I have my excess runoff, the water that is not infiltrated, and then I will convert that to acre feet. So I'm going to use a time period of 1 hour. So that means I'm going to start my first interval at 0. It's going to end at 1. My beginning F using the equation is 12 inches per hour. At the end of that interval, it is decreased to 3.27 inches per hour. If I average those two values, I get 7.64 inches per hour of infiltration. My rainfall intensity was 2 inches in that hour. So that is well below what I'm estimating to be my infiltration using the Horton model. So there's no excess rainfall. All of it is infiltrated. So there's nothing that becomes runoff in that first hour. Look through the second hour. So I'm going to start at time 1, end at time 2 hours. This will begin with 3.27 inches per hour. It ends with 1.48 inches per hour. My average here is 2.38. My rainfall was 4 inches per hour. So that gives me an excess amount of rain of 1.38 inches. Converting that to acre feet, I am going to get 11.5 acre feet. So from hour 2 to 3, we had an average infiltration of 1.29 and a rainfall of 6 inches in that hour, giving us 4.71 excess inches of rain, which is 39.25 acre feet. I'm going to go ahead and fill in the rest of this table, and then we'll talk about the end. The total excess water that was not infiltrated but became runoff is 58.58 acre feet of water. And when we did the first method, the index method, we got 50 acre feet of water as runoff for this same watershed. So that concludes the introduction to these first two methods for estimating infiltration using the index method and the Horton model method.